Okay, today we're going to cover lesson 4 from chapter 3. And today we're going to see several definitions and theorems about perpendicular lines. So it'll be proofs with perpendicular lines. So the first thing is talking about the distance from a point to a line. And the distance from a point to a line is going to be the length of the perpendicular segment from the point to the line. This perpendicular distance is always going to be the shortest distance between the point and the line. Now, technically, what I could do here is I could draw a line segment that would go from point A down here to point K, or even over here. But just keep in mind that this segment down here from A to B, this perpendicular segment is going to be the shortest distance from point A to line K. So keep in mind, let's say that, let's turn this into, let's say you have the banks of a river, and let's say this river is alligator infested, and you want to get across that river the fastest way that you can. You're not going to swim from here to here or from here to here. The fastest way to get across that river would be the perpendicular distance. So just know that the fastest way or the shortest way from a point to a line is going to be the perpendicular segment. Now, in this lesson, the next example we're going to do is we're bringing back the distance formula. So if it asks you to find the length or the distance from a point to a line, we're always going to look for the segment that has the perpendicular or the right angle marking on it. So that's what we're going to do on the next slide, is we're going to actually use the distance formula. So take a look. So notice here, it's asking us to find the distance from point A to line BD. Notice there are 3 line segments coming out of point A over here. But again, remember, the distance is always going to be the perpendicular segment. So I need to find the length of AC. The distance would not be from point A to point D or from point A to point B. That would not represent the distance from point A to line BD. It is going to be line segment AC. And the reason why I know that is because AC, let me write that in here. So because AC, that segment, is perpendicular to BD, the distance from A to BD is going to be segment AC. Now, in order to find how long this distance is, I need to bring back the distance formula. So just to review from the previous chapter, the distance formula is this. And it's going to be, we'll just represent D as distance. And it's, remember, it's x2 minus x1 squared plus y2 minus y1 squared. And remember, this was all under the square root. So what you're going to be using when you're using the distance formula is you're going to be given 2 order pairs. Order pair number 1, which includes x1, y1, and then order pair number 2. Again, think of those little numbers as labels. They're subscripts. They're not exponents. So now let's try to find the length of that red segment, AC. So go ahead and do it down here. So the 2 order pairs that I'm using are going to be the order pair for A, which is -3, 3, and the order pair for C, which is 1, negative 1. Now, if it helps you to label which one is x1, y1, and which one's x2, y2, you can do that. You don't have to. I'm going to go ahead, and it doesn't matter which one is which. I'm just going to say that my ordered pair for A is going to be x1, y1, and C will be x2, y2. So let's plug it into the formula. So I'm going to do 1 minus negative 3 squared plus, then I take the y's, negative 1 minus 3 squared, and it's all under the square root. This is going to give me the length of AC once I subtract, square, add, square root. So once I do this first parentheses, this really turns into 1 plus 3. So this is 4 squared. This really turns into negative 4 squared. So this is negative 4 squared. I'm going to square them, add them, and square root. 4 squared is 16. Negative 4 squared is 16. I'm going to add them. Now we're not using a calculator, so then we're going to leave this in simplest radical form. So what we need to do here is break down the 32. So I'm going to break this down. Let me stop. Okay, so I need to break down the square root of 32. Now, for those of you who are good at recognizing a factor like 16 times 2 is 32, then you could go right into 4 square root of 2, which is going to be your answer. However, let's say instead you didn't do 16 times 2. Let's say you did 4 times 8. Then you'd have to keep breaking down until it's prime. And then break this down. And break this down. And now we've got a pair. We're going to make our pairs. Pair of 2's, a 2 comes out. Pair of 2's, a 2 comes out. And then you leave that one under the radical. We're going to multiply these back. And notice it's the same answer as if I would have just realized I had a perfect square there. So since more than likely we'll leave our answers in simplest radical form and not in decimal form, you would simplify this and it would be 4 square root of 2. Now, let's say it's a word problem and they want you to approximate it and round it to the tenths place. Then you would get out your calculator, hit the square root button, and then you would get, I think it's 5.7. It's like 5.65. You'll round it, and it's approximately 5.7. However, on the test, you're going to be leaving it in simplest radical form. So if you're not aware that you had to look for the segment that had the right angle, you would get this wrong. So if you instead used AD or AB, it would be wrong. It has to be the perpendicular segment. Pretty good there? All right, let's see what a perpendicular bisector is. Now, we've already talked about bisectors. We talked about segment bisectors and angle bisectors. So here, the perpendicular bisector of a line segment PQ is the line N with the following two properties, where N is perpendicular to PQ, and then N is also going to pass through the midpoint, which is point M, of PQ. So remember, when we bisect something, we can't bisect a line. We have to either bisect an angle or a segment. However, the thing that's doing the bisector, this thing right here, can be a line. Because remember, when something is being bisected, it creates two congruent pieces. So that's why PM has the marking here, and it's congruent to MQ. Pretty good there? So a perpendicular bisector, again, you're going to be looking for the right angle marking. Next, we're going to see several theorems. The first one is the linear pair perpendicular theorem. And what this one states is if two lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. So here, if they told you that angle 1 was congruent to angle 2, then we know that G is perpendicular to H. So we've seen linear pairs. So for example, you've got your straight angle or your straight line, and then if it's split into 2, and this one, they're not congruent, so this is how I can tell the difference, that this segment here, or this ray, is not perpendicular. Maybe, let me make it a line. So this would be like 110, and this could be 70. These would not be congruent angles, so then this would tell me that this line G is not perpendicular. So in order for it to be perpendicular, angle 1 and angle 2 have to be the same, and they would both be 90. So this is the linear pair perpendicular theorem. So when it creates two congruent angles, then we know the lines are perpendicular. So in order for this theorem to work, you're going to have two lines. And if when the two lines intersect, then, and if it creates two congruent angles, angle 1 and angle 2, then I know that if I take that 180 and I divide it by 2, that tells me that both angles are 90 degrees, which makes them congruent, which also makes the lines perpendicular. So if it were just a linear pair and it was divided like this, and they weren't congruent angles, then these lines wouldn't be perpendicular. That's what I was trying to show here. The next one is Indicua transversal theorem. And then this one just says that in a plane, if a transversal is perpendicular to one of two parallel lines, then it's perpendicular to the other line. So here they're going to be giving you that two lines are parallel. Notice the little red arrows. So if it's perpendicular to one of the two parallel lines, then it's perpendicular also to the other line. Because think about it, if you've got parallel lines here, and if this is your transversal, then this angle here is corresponding to this angle here, which would then make angle K, or not angle K, line K, perpendicular to line J. Even if we did it over here, alternate exterior angles are congruent, so then the lines are parallel and then they're perpendicular. Notice once you have one right angle, the other 7 are also going to be right. Next one. Now back in lesson 3.3, on that slide where I talked about ways to prove lines parallel, so far we learned that if we could show corresponding angles congruent, alternate interior angles congruent, alternate exterior congruent, or consecutive interior supplements, then what I can do is show that lines are parallel. This is the last way that I talked about when I was in 3.3, that you can also show that lines are parallel by saying if two lines are perpendicular to the same line, then they're parallel to each other. So this is a way that you can prove that the lines are parallel. And again, we've got, if these are the parallel lines, maybe I'll do them in green, and then this is the transversal, then here, these are corresponding angles and they're congruent, which by the converse makes them parallel. And now we can also say by the perpendicular to a transversal theorem to show that they're parallel. And then the last slide is just an example. It's like a real life example. So here is a photo of a layout of a neighborhood. It wants me to determine which lines, if any, must be parallel in the diagram and explain your reasoning. So let me zoom in here. So I notice I have a bunch of lines here. I've got line S, T, U, P, and Q. None of them have the little arrows indicating that they're parallel, but I do have right angles in here. I've got a right angle marked here, and here, and then here. So now I need to figure out which ones are parallel, and I'm going to apply some of the theorems that I just learned. So if you notice that lines P and Q, which are here and here, are both perpendicular to line S, which is here, I can use the lines perpendicular to a transversal theorem to show that P and Q are parallel. Let me write this in words. Okay, so lines P and Q are both perpendicular to line S. So, by the lines perpendicular to a transversal, P and Q, and that's a theorem, P is parallel to Q. And then if I look at it another way, I've got it also this other right angle over here. I should do it in green. This one. So then what I can also say that S and T, which are, here's T, S and T are both perpendicular to Q, and Q is here. So they both have right angles right here and here. So because S and T are perpendicular to Q, I can use that same theorem, the lines perpendicular to a transversal theorem, and I can say that S is parallel to T. Let me put this in words. So lines S and T are both perpendicular to Q. So by the lines perpendicular to a transversal theorem, I can say that S is parallel to T. So from the diagram, I can conclude that P is parallel to Q and S is parallel to T, and they're both using the lines perpendicular to a transversal theorem. So that is it for lesson 3-4. You do have a short assignment. It's due on Tuesday, no school on Monday. It is a teacher work day, so that assignment is due on Tuesday. And then on Tuesday, we're going to start section 3.5. Now 3.5 is going to have a lot of your Algebra 1 skills. We're going to be doing slope again, because what we're going to see in section 3.5 is that when two lines are parallel, they have the same slope. When they're perpendicular, they're going to have opposite reciprocal slopes. So that's what we'll cover on Tuesday. And then we'll spend a couple days on that. We will probably have a test that first week of the second quarter. So nothing next week. Next week is the end of quarter one. So once I put the test grades in, that should be about it. You'll have a homework grade or two, but no more major tests or quizzes for quarter one.